This is 2018 AMC 12B, problem number 21, and here is a view of this problem. We're given actually a right triangle. How do I know it's a right triangle? From the side lengths, which is a typical right triangle, where AB is 13, that would be the hypotenuse, right? So 13 for the hypotenuse, AC is 12, BC is 5. I did an earlier sketch. A few things to remind you. We have a right angle here. Obviously, it would subtend on the circumcircle the diameter, right? So it would subtend a 180-degree arc, which is associated with the diameter. As a result, the center of that circle, which is the circumcenter, will obviously lie on the midpoint of AB, both the hypotenuse of the right triangle and the diameter of that circle. So we already know where our point O is. And obviously AO and OB are equal, and the radius, the circumradius of that circle is 6.5, 13 over 2. Further, I also need the in-center. So in-centers are always not nice. So how do you draw that? Well, one thing I know for sure, it will be the in-circle would be tangent to the legs of that triangle AC and BC. As a result, it would lie on the 45-degree line. So probably it might be a better idea to first draw the 45-degree line, I guess. So you have this 45-degree line, and now I can speculate where the center of that, yeah, probably here I would say, but I can make some correction as well if necessary. But yeah, so that's our in-circle. And then, well, the main question, we draw a circle centered at M, which is tangent to the two legs of AC and BC. Wow, again, tangent to the two legs, again, the center M of that circle would lie on that 45-degree line, right? So when I say 45-degree line, I mean the angle bisector of angle ACB, right? That 90-degree angle, I'm splitting as 45 degrees each. And so we need a circle which is tangent to AC and BC such that it is also tangent to the circumcircle of triangle ABC. Now that is something to ponder upon. Let me go ahead and draw a new picture, a different color. So where is the center of that circle? I don't know, to be honest. Looks like it will be somewhere here, right? So, or maybe a bit outside, I don't know. Yeah, well, let's try, yeah, maybe a little bit outside, so just give me a second. Yeah, so probably somewhere here. So we have this point M. So this point M is on that 45-degree line, and somehow this distance here is equal to that distance. So when I keep drawing my my circle, not only it will be tangent to the two legs of that right triangle, it will also be tangent to the circumcircle. And but where exactly? Where? Okay, so this is a very well known feature. Whenever you have two circles which are tangent to each other, internally or externally, doesn't matter. For instance, consider these two circles. These are the centers. Obviously, hey, this is a very well-known property. The two centers, the point of tangency would lie on the line segment joining the centers of these circles. The same thing will apply to two circles when they are inside each other, right? So for instance, consider this one. So these two circles must be such that their centers and the point of intersection are aligned, right? In fact, this you can think of these two circles, especially, well, in this case it's more obvious, they are in dilation, right? So there's a homotety between this circle and the bigger circle, such that the center of homotety is this point, and you can expand that little circle until you hit the big circle, basically. But then, with that observation, it's clear where the two circles will intersect. They will intersect on that line segment joining the centers of those circles. Boom, just like that. I'll call this point of tangency as T. And let me go ahead and use my lasso effect. I wonder what this was probably named after somebody named Lasso, I guess. Well, silly claim. Okay, but anyhow, so going back to our problem now, we did quite a lot of stuff, right? So I came up with this very nice construction, looks like to me. I don't know how it looks to you. So I located my in-center I. One thing that you might worry is, hey, where is the I? Before I go into coordinates, let me go ahead and quickly calculate the in radius the radius of that green circle. We can easily do by calculating the area of our triangle ABC in two different ways. Well, we can focus our attention on the legs AC and BC of this triangle, and one way to calculate it would be as such. So that would give us 60/2, which is, I believe, 30. An alternative way to calculate the area of this triangle ABC is to split it into three parts, into CIB, three triangles, right? BIA, and then AIC. And obviously, we can quickly realize that the area of triangle CIB is just equal to CB, the base times height. Well, obviously the altitude of that little triangle. Okay, I don't want to mess up with my picture too much, but just for the first one, let me go ahead and draw that tiny triangle. But I hope it will be clear. So the base BC times the altitude. The altitude is just R, right? And then divided by 2. And the same thing will apply for the others as well. AB times R/2, and AIC would be AC times R/2, and boom. Wow, we actually, we can factor out R/2, AB plus BC plus CA, and we actually proved a very well-known result. R times AB plus BC plus CA is the perimeter, divided by 2 is the semi-perimeter. We just proved an alternative area formulation here, and here the semi-perimeter would be, let's quickly do it, R times, 5 times 12, sorry, 5 plus 12 plus 13, which is 1830, divided by 2, 15. Hey, earlier we found out the area was 30, so we kind of did a double counting here, right? With that simple type of argument, we can easily establish that R is indeed equal to 2. And now I'm ready to use some coordinates and some coordinate bashing. We need to find a good point to serve as the origin of our coordinate plane, and obviously a natural candidate would be the point C, right? Because of that right angle. So I can just extend this. So this would be like my x-axis here, and this one would serve the purpose of the y-axis, and the point C has coordinates 0, 0. The point B in that sense would be 5, 0, and A would be 0, 12. And by the same token, O, which is the midpoint of AB, would be 5 plus 0/2, which is 2.5, and 12 plus 0/2, which is 6. Okay, awesome. How about I, the circumcenter here? We just realized that the in radius is 2, so this altitude is 2, this portion is also 2, so therefore I has coordinates 2, 2. Right? Does that make sense? Let me go ahead and create some space for myself. And so the coordinates of I is 2, 2, obviously. We already established O is 2.5, 6. So therefore, one way to finish the problem is to identify the coordinates of the point M, right? So That would be super cool. But one thing is, we know that M is on the 45-degree line, right? So in that sense, it would be, the coordinates would look like XX, right? Does that make sense? And indeed, when we use coordinates, that 45-degree line has a special name. It is y equals x. Now, how can I establish the coordinates of the point M? Multiple ways, but probably arguably one of the simplest ways to finish would be to let me go ahead and use probably the black color. Let me expand this picture slightly so that everybody can have a clear view of this. What I'm planning to do is to drop two altitudes from the point O to the two sides, and when I do so, I realize that I have a right triangle here, that tiny triangle, which is a right triangle because we have parallel lines here, and these two lines are parallel. Obviously, we have a right angle there, and I will go ahead and use pi tag on that right triangle. Obviously, so this distance here is just equal to this distance, but we know the coordinates here is x. Oh, sorry for that. So the 12 here is the whole AC, so this one has coordinate 6, and the whole thing here was 5, meaning this one has coordinate 2.5. Okay, so therefore, do you agree that this distance is just 6 minus x? And similarly, this distance here, this one is x as well, so it is just x minus 2.5. And applying pi tag, I can easily find an expression for the distance OM. All right, so let's go ahead and do that. Let me just keep this size, I guess. OM squared is simply equal to the 6 minus x squared plus x minus 2.5 square. And that will give us the distance OM, right? So actually you can, if you want OM, so we can directly just take the square root of both sides and boom. And let me just simplify this slightly. So we have 36 minus 12x plus x squared plus x squared minus 5x plus 6.25, I believe, 2.5 squared. All right, and you can further do some modifications. Because before I do that, remember that earlier I mentioned how the red circle, the circle centered at point M, and the circumcircle are in homotety with respect to each other, and the center of homotety is T. As a result, OMT is collinear, right? So OMT collinear, and as a result, we can try to calculate the distance OT as the sum of OM and MT. Does that make sense? And that would do the trick. Obviously, the radius of that red circle is just that distance x, right? So MT is just x, and OM we just calculated it just a minute ago. How about OT? Well, OT is just the radius, the circumradius of our triangle ABC, but earlier, like we did, we calculated it to be 6.5 as well. So therefore, we are pretty much good in that case. So therefore, we have this expression for OM. So let's just express OM as the difference between OT and MT. We established that OT, which is the circumradius, is 6.5, so therefore 6.5, or let's just write the formula first, OT minus MT is just equal to OM, right? So that's the expression I'm going to use. So OT, like I said, is 6.5, this is the circumradius, minus MT is just x, the unknown that we want to figure, and OM is just this radical expression. And I don't want to just focus too much on that. So we would have 2x squared minus, I believe, 17x, and then some extra stuff, 42.25. Well, I'll go ahead and quickly square both sides and then do the necessary manipulations. Actually, once you square both sides, you get rid of the square root expression, and life is not that bad. So 6.5 squared minus 13x plus x squared is equal to 2x squared minus 17x plus plus well, actually I could have even left this one. Well, okay, let's just keep it, I guess. 42.25. Actually 6.5 square is also not too hard to square, right? If you know the squaring trick for two-digit numbers which end in 5, that would be so it would be we'll say 6 times 7, 42. Yeah, 42.25, right? So if you will, yeah, let me just put it like this, 42.25. There you go. Am I high? Oh yeah, I love that. Look at that. These two just cancel each other. So wow, so that's just, and then the x squared will disappear with this one. So we will have x squared, is that minus 4x, is equal to 0, or if you will, x times x minus 4 is equal to 0, and boom, x is indeed equal to 4 is one of the solutions, right? Well, actually the only potential solution. Well, yeah, we found the coordinates of the point M now. The question is asking for the area of triangle MOI. This triangle here, MOI. Let me go ahead and rewrite these coordinates here. So we have our triangle. Let me create some space here probably. So we have our point O, the point M here, and the point I. And we know the coordinates here. This one turned out to be 4, 4. This one was 2.5, 6. And finally this one is 2, 2, I believe. So how can you find the area of this triangle? There are multiple ways you can do it. You can obviously use a shoelace formula, which is probably one of the faster ways to handle it. Shoelace. Well, obviously you just list the coordinates. Let's start with 4 probably. 4, the x coordinates. I'm listing the x and the y coordinates of the points in a in any direction pretty much, because I'm going to take the absolute value regardless. So 4, 2, 2.5, and then we do the same thing. Actually, I will need one more, so I will repeat the 4 at the end, and then the other one, the y coordinates are 4, 2 again, and then a 6, and then I bring back the 4 here. And if you guys all remember, so we would just multiply these two and then add the product here and then this product, and then we would simply subtract these products. Does that make sense? So let's go ahead and quickly do that. So the area of our triangle OMI as a result would simply be equal to 4 times 2 plus, well, actually, okay, so the formula, the shoelace formula comes with a 1/2, if you guys remember. So 1/2, okay, there you go. 4 times 2. Actually, just to be on the safe side, let me just, don't forget to keep the absolute value as well. So 4 times 2, plus 2 times 6, because I think orientation eventually matters if, yeah, so 2.5 times 4, that's right, minus 4 times 2, the red ones, 4 times 2, 2 times 2.5, 2 times 2.5, and finally 6 times 4. Well, I guess this one will come out negative for sure. Good that we kept the absolute value, right? So that whole thing is just equal to 1/2. Absolute value of, we have 8 plus 12 plus 10 minus 8 minus 5 minus 24. And that's just 1/2. Absolute value of the positive ones are 30. The negative ones are 32, 37. And that's just minus 7. So in absolute value, it will be 7. And boom, 7/2 is the correct answer. There you go. A couple of more remarks. If you didn't see that, if you forgot about your shoelace, which you shouldn't, obviously, an alternative way would have been to use to drop a perpendicular here and find this distance, and then apply and then you can find the area by just calculating the distance mi, which is obviously 4, 4, 2, 2. So you know that this is 2√2 here, right? So all I need is the distance from the point O to IM. IM is on the 45-degree line, namely the line y equals x. So we can use the distance formula basically. So the distance formula, when you apply it, I don't know if you guys remember how to use it. We have y minus x is equal to 0, and we want to calculate the distance from this point, 2.56. So therefore the coefficients here are 1 and minus 1 square, and all we do is we plug in these two values into our equation. 2.5 minus 6 plus 0, pretty much. There's no constant here. It goes through the origin. And boom, so we have 3.5 on the numerator. On the denominator, we have root 2, I guess. And then we can rationalize it. So we have 7 over 2 root 2 over 2. And that's just give me 7 over 4 root 2. Now we can go ahead and recalculate the area one more time. OMI is just 1/2 times base is 2 root 2 times distance is 7 over 4 root 2. And so root 2, 2, they cancel, and then this one there's a 2 remaining, and boom, you have 7 over 2. All right, so this is a coordinate solution. Now let's entertain ourselves with an alternative look into this problem. So what I mean is, can we provide a more synthetic way of handling this situation, or at least figuring out where the coordinates of this point would be. Well, okay, so for that you need to realize that this red circle has a special place with respect to our triangle and the circumcircle. Indeed, this triangle has a special name in literature. It's called the mixtilinear incircle. For those of you who are, well, obviously preparing for the Olympiads, I mean, this is standard. And if you have Evan Chan's book, which I highly recommend, Euclidean Geometry for Math Olympians, that would be section 4.8 in that book. There's a very nice description and very important features of both the mixtilinear incircle and the generalization, which is the curvilinear incircle. It turns out that whenever you have a mixtilinear incircle, the incenter has a special location with respect to the mixtilinear incircle, and it turns out that this location is just the tangency points, this point here and this point here. It turns out to be the midpoint on of the line connecting these two. So let me go ahead and do that. So if I let's augment the picture slightly. So therefore, if I just focus my attention on these two tangencies of the red circle with our triangle ABC, and I just join this line, not only this line go through the incenter, which is a property of the curvilinear incircle, right? But the mixtilinear incircle is even stronger than that. Not only it is the not only it's on this line, it turns out to be exactly the midpoint of that line segment in the case of a mixtilinear incircle. So if it's curvilinear incircle, you have on the line. But when it's mixtilinear, well, obviously I didn't define curvilinear. I'll just leave it to you to read Evan Chan's awesome book, Euclidean Geometry for Math Olympians. But then this resolves the problem of finding the coordinates of M just like that. So if this is 2, 2, the coordinates of I, so therefore the coordinates of M obviously will be, because 2 is the midpoint between 0 and x, so therefore x must be 4, and the same thing here too. Boom. So, well, you might argue that, hey, did it really help us? All it did is just saved us with this much algebra. Well, remember, this is the AMC, right? So you have just the AMC 10 or 12, doesn't matter. You have pretty much 3 or 4 minutes per question, and so this saves a lot of work. And in this case, we were kind of lucky because look at these ugly expressions; they just cancelled very clearly. But that's another nice feature of this problem. Well, I hope you enjoyed this solution, and looking forward to see you guys in our next lecture.